Okay, great. Firstly, thanks to Professor Ma and the HKU team for hosting this great conference. For me, my name is Yang. Today, let me introduce some of our research techniques to share how can we make AI run faster. Yeah. Yeah. Firstly, I'm sure you know this very well. In the last 5 years, we can see our models, especially the state-of-art AI models, are becoming larger and also more computationally expensive, right? We have some model with more than 1 trillion parameters, but like in 2017 or 2016, the best model like ResNet 50 only has 25 million parameters, right? So that's very crazy. Especially, it's very expensive to train. It's computationally expensive. So for my background is high performance computing. So the idea of high performance computing is to make the computation faster. For here, we want to make the training and the inference of AI models faster and more efficient. For today, we know the training AI is kind of empirical study, right? So my current research is to develop empirical methods, make AI faster and more efficient. But we also had some convergence study in our paper. If you like, we can talk after this presentation, right? Today I want to share three different methods to show you the idea how can we make AI more efficient and faster. Firstly is system level techniques. Okay, sorry. Yeah. I want to show you a figure. For this figure, the horizontal axis is a sequence length or sequence position. The vertical axis is uh, actually it's the loss. Lower is better. For the vertical axis, lower is better. So here the idea is today almost all the AI models like ChatGPT, like Anthropic, like also Google Gemini, they are using long sequence model, right? The sequence length, for example, for the Gemini 1.5, the simple sequence length can be 4 million, right? So the context length, the context length is very long. Why? Because with longer sequence, often you have better results and the model is better. That's why today all the models they are processing long sequences. However, the concern is the sequence is longer and the memory cost is higher. So here there are some notations. So B is the batch size, how many sequences for each batch. H is the number of heads. N here is the number of tokens in the sequence, right? So we know we need to compute the attention score. The Q matrix is n by d, right? The K matrix is d by n. So the QK matrix is n by n matrix. So the memory cost is B by H, B multiplied by H by N by N. So it's a kind of quadratic cost, quadratic memory cost, right? And so that's a big concern because N can be 1 million, N can be 4 million. In the future, may N can be 10 million, right? So this is a significant memory overhead. Okay. So, and also here is some data. The horizontal axis is sequence length. The vertical axis is memory cost for training GPT-J. Right? You see, when the sequence is very long, the memory cost is huge, right? Okay. So the naive or straightforward approach is to partition the sequence length, right? So you have multiple servers or multiple GPUs. You partition the long sequence to different GPUs or different servers, right? That's a very straightforward idea. However, the concern is if we just use this straightforward implementation, partition the sequence to different GPUs or different servers, we have to finish all-to-all communication, right? Because for transformer, for the attention structure, so every token needs to do the computation with all other tokens, including itself, right? So here, some tokens on server one, some tokens on server two, other tokens on server N or GPU one, GPU two, GPU three, right? So all different devices or servers, they need to do communication. That's auto communication. That overhead is huge. So here, how about I show you an example? Assuming we just have four GPUs, but you can have 400 GPUs, right? 4,000 GPUs, even 40,000 GPUs. The same idea. So here I just use four GPUs to make it easy to visualize. So here B is the base size, S is a sequence, H is heads, right? So we have three dimension for the data. You see? Now let me share a simple trick. How can we make the communication overhead lower? Firstly, how about on each GPU or each device, we do some local computation to finish computing all the attention score for the local tokens, right? For example, in total, maybe we have 4 million, but on each GPU, we only has 1 million token, right? How about we finish the first 1 million token to token, right? And then for the next step, for every step, actually, we send all the key to our right-hand side neighbor and get a new key from our left-hand side neighbor. And then we do the local computation again. And then the same thing, we send all the key to our right-hand side neighbor, get a new key from our left-hand side neighbor. And the same thing, right? You see here, no bandwidth compensation, right? So every step, so every GPU is moving some data and also can receive some data, and also they can finish the computation concurrently at the same time, right? So the idea here is we transfer the key embeddings and value embeddings in a ring, and in this way, no computation on the network, and also they can do the computation at the same time. Also, they can reduce the memory cost. So here, firstly, I want to show you the results for the memory cost. So here, the big N is the number of devices or number of GPUs, right? N can be 1,000, N can be 2,000. So the small n is the number of tokens in the sequence. You see, so the baseline is n squared, right? So now the range of attention is n squared over big N, which means we can significantly reduce the memory cost. And also for the communication cost, because as I mentioned, no bandwidth computation. So firstly, the naive all-to-all is kind of the computation, the communication time. Communication time is roughly n squared and big N squared. But for the ring itself, tension is just order of n, right? It's much lower, right? That's why it's much faster. And also here are some of the empirical results. So here, the colossal AI means our methods, and the Mectron means the baseline. You see, with the same number of GPUs, we can get a higher throughput, and also with same number of GPUs, we can use a longer sequence without memory memory issue, right? Often, if we use a very long sequence, we have the OOM issue, right? Now we can maximize the sequence length per GPU. Okay. Okay. So here the idea for ring self-attention actually is from the ring O-reduce proposed by the founder of Anthropic. Uh, he was in Baidu actually in 2017. So the idea of ring O-reduce, right? And even roughly 8 years ago, they trained some models in Baidu Silicon Valley. So here is a difference. So for the okay, sorry. So for the ring self-attention, actually here we have the global dependency. Right? We need to preserve the global dependency, so it's more complicated. Also, it's mixed of communication with computation, and also we needed to deal with the softmax normalization. That's why it's a little complicated for implementation. Okay, so to the best of our knowledge, so we are the first team to propose the sequence parallelism for transformer models, right? So these institutes, they either cited our paper or they use our implementations. So the second part I want to share is algorithm techniques. So I want to introduce a method. The name is pyramid attention broadcast, PAB. Yeah. So for today, we know the video generation models are very expensive. Not just training the model. If you just deploying the model for the inference, the cost is also very high. So here, how about you use one H100 GPU? How about you just use one billion model? You generate a 10-second 720p video. Right? So the model is small and the video is low quality, and also it's a very short video, right? So even for this kind of setting, can take you 6 minutes, right? So, but I mean that's just the beginning, right? In the future, we may need to generate a video with several minutes and also larger models, right? So now the question is, how can we make it faster and more efficient? So we know we already have many tricks, right? Like we can use pruning, right? Pruning to make the model smaller. There are many tricks I mean, the sparsity tricks make the model sparse to make the model faster, right? And also there are some tensor parallelism or data parallelism and many different kind of parallelism tricks, right? So here, can we invent some new techniques orthogonal to the existing techniques, right? Can we furthermore make it faster, right? That's the idea. So here, how about let me share a very interesting figure. So for this figure, the horizontal axis is a diffusion step. Right? The vertical axis is the attention difference. Right? So from step 1 to step 2. how different is attention, right? From step 2 to step 3, from step 3 to step 4, and step 5, step 4 to 5, and then 5 to 6, 6 to 7, right? How different, right? Because we know for the diffusion model, you can have 100 steps, right? You can also have 200 steps, right? Denoise, 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 add noise, add noise, add noise, right? It's just many different steps. So here we are making a better attention block, right? Or a block of parameters by so many steps. So how the parameters are changing. So here is a visualization. You see, we found something very interesting. Firstly, 70% of the steps in the middle, the attentions actually are very stable, right? For example, you have 100 steps. Maybe from the number 1 to number 15 steps, they are changing dramatically. But in the middle 70 steps, they almost no change, only minor changes in these 70 steps. And also, the second pattern is the spatial attention is changing faster, and for the cross attention, almost no change, right? So for here, assuming all the attentions, they are changing slow in the middle, but spatial attention is aggressive, and the cross attention is very stable. Okay, that's the second pattern, right? So now our idea is because they are changing slow, I mean almost no change, can we reuse, right? Can we reuse attention? Right? Because almost no difference, we can avoid some computation. That's the idea. So the implementation is here. So we have three kind of attention: spatial attention, temporal attention, and cross attention. Right? We know the spatial attention is very aggressive, right? So we just reuse it once, right? We compute the model once, we use it for 2 times, right? And for the cross attention, it's very stable, right? You can use it 5 times or 6 times. We do the computation once, we use the cross attention for 6 times or 7 times, right? And for the temporal attention, maybe we do the computation once, we use it for 3 times. I mean, you see for different attentions, we have a different broadcast range, right? In this way, it's like, I mean the structure or the broadcast range, just like a pyramid. Okay. So, and we can just broadcast the attention outputs, right, to make it easy to implement. So, and another advantage of this is we can avoid the sequence parallelism, right? As I mentioned in the first part, the sequence parallelism can be a huge overhead. If we can broadcast everything, no need to do the computation, and also no need to do the communication, right? The same idea. Okay. So in this way, firstly, on just if you on just on one GPU, we can have 30% speed up, right? Roughly 1 point time speed up. But you put this on multiple GPUs, for example, 8 GPUs, it's possible you can get 10 times speed up because firstly, we minimize the computation. On multiple GPUs, we can also reduce the communication overhead, right? For one GPU, only computation saving. But on multiple GPUs, you have the uh, computation savings and also communication savings. That's why it's possible to achieve 10 times speed up, right? Uh, but I won't say because we make it faster to find a balance or trade-off between the accuracy and the speed, right? We need to make sure we get roughly the same quality, right? So here you see we generate the same video almost uh, the same, right? The quality is roughly the same, but it's faster. You see here are some demos. Yeah. So here also some demos we get the same output but much faster. Okay. Yeah. So the takeaway for this is we can reuse some attention outputs, right, to make it faster, and because we can avoid some computation and also avoid the communication, the sequence parallelism, right? Okay. I mean, this paper was published in NeuroNews. So we got, I think, more than 2,000 stars on GitHub. Right. Okay. And the number three part is optimizer level techniques. So for here, let me show you some results. So in the year of 2017, right, when the model was not very large, often we can put the model, the whole model to the GPU, right? Like Res 50, you only have 25 million parameters, right? It's very easy. You can, I mean, have a copy in each GPU, right? I think in the future, eventually, the model cannot be very large. I mean something like 10 years later. So maybe you still have the 10 trillion model, but your GPU memory maybe is much higher than today. So I think that possible we can just use data parallelism. Basically for data parallelism, we just partition the data sample to different servers or different GPUs. For here, how about, sorry. How about I assume we only have three, three servers or three GPUs, right? You have six data samples. For data parallelism, you just partition the data samples to different GPUs, and then you compute the local gradients, and then you do an average, an or reduce operation to get the global gradients and send the global gradients to all the servers. And each server can use the global gradients to update the local weights. Right? In this way, you can make the computation finished. Right? It's just data parallelism. So why data parallelism is so efficient? Because we increase the number of GPUs, we increase base size, right? Assuming here 512, 512, the base size 512 is the best base size for one server or for one GPU, right? You have one GPU, the base size is 512, and for two GPU, best base size should be 1K, and four GPU, 2K, and eight GPU, 4K. And eventually, you can maximize the base size, max number of GPUs. You can minimize number of iterations. That's the ideal situation. However, the concern here is by training the same number of epochs, if you maximize the base size, right? So here an example, base size is 8K, baseline is 256. Even we train the model by the same number of epochs, our accuracy is much lower, and also it's not stable. It's accuracy lower and also not very stable, you see. So, and the why, uh, I think so there are many studies. So here I just want to show you one possible explanation is a sharp minimum problem. That means so for the baseline, like the base size is 300 or 200, right? So your training accuracy is high, your testing accuracy is also very high. So the generalization is very good. But for live-based training, so even your training accuracy is very high, but the testing accuracy can be very low. So for here, we want to offer techniques to make this better. So firstly, I want to share you a pattern. So how about I use AlexNet to visualize this because AlexNet only has 8 layers. It's easy to visualize. So for each layer, we compute and the norm of the weights. And also we can compute the norm of gradients. We can also compute the ratio between the norm of weights and norm of gradients, right? Now we can see something very interesting. For this ratio, the number 6 layer is very high. But for the number 1 layer, this ratio is very low, right? That's very interesting. So if we use the same global lane rate for all layers, layer 6, we need a huge lane rate, right? But layer 1, we need a tiny lane rate. If we use the same lane rate for layer 6 and layer 1, layer 6 may converge very well, but layer 1 may diverge. Right? So that's the idea for trust ratio. So we need a trust ratio actually to control different the lane rate for different layers at different iterations. Now, how about I just use the idea of trust ratio with momentum SGG, right? Momentum stochastic gradient descent. So for each layers and each step, we first compute the gradients, and then we initialize this trust ratio. We compute the norm of weights, we compute the norm of gradients with VDK, and then we use trust ratio to update the momentum, we use trust ratio to update the weights. Right? Let me introduce the algorithm first, and then I show the results. Then I explain so why this is good. The same idea, we can also add the first momentum, second momentum, just like Adam, right? To use the trust ratio for the Adam optimizer. The difference is just the first momentum, second momentum, right? And now, after we use the techniques of trust ratio, so the first figure, the horizontal axis is the number of epochs. The vertical axis is testing accuracy, right? You see, now in the same number of epochs, we can get the same accuracy. And also for the second figure, right? We achieve the same accuracy. We can minimize the number of iterations, right? We can maybe use 10% of iterations to get the same accuracy. And in this way, we can achieve linear speed up. So why this works? I think there are several reasons. So here, the first reason is, how about let me show you a figure. So this is a 3D figure. The first dimension is the horizontal dimension. The first dimension, the horizontal dimension is value of the trust ratio. The second dimension actually is vertical dimension is a number of, is a iteration number, and also there is number 3 dimension. So how many trust ratio in this range? You see, in the beginning, almost all the trust ratios are tiny. That means that's a natural per layer warm-up. And also across all the iterations, we can see some trust ratios are tiny, And also, we don't know which layers are tiny, which layers are huge. That's a dynamic, sorry. That's a dynamic per layer one mark. You see, in each iterations, we can maximize the lane rate across all iterations without diverge. Okay. So the first takeaway is Lars and Lamb. So trust review techniques can maximize the global lane rate, which can make the training faster. And also, trust ratio is the inverse of the Lipschitz constant, right? Which means, so when the landscape of optimization is smooth, we can learn fast. And when it's not smooth, and we should learn slow, right? I mean, some layers, they are smooth, other layers, they are not smooth, and they are in the same iteration, right? That's why we can dynamically control the learning speed or learning rate for different layers. Yeah, so the LAM and the LARS can offer us the best real-time navigation for optimization. Yeah. In this way, we can reduce the ImageNet training time from 30 hours to roughly 30 seconds. Right? Yeah. And also, this was also used by Snapchat. They use LAM to train their Snap video model, their video generation model. Right? Yeah. So there are some very crazy results. This is a screenshot of NVIDIA public GitHub, right? So according to NVIDIA, so the LAM can be 17 times faster than ADA, right? You see, that's not my GitHub, right? That's NVIDIA GitHub. So can be very efficient, can be 17 times faster. Yeah. And also, so according to Hugging Face, so the most downloaded AI model by June of this year was Facebook's MobileNet V3, the most popular model in the world. This model was also trained by my LAM algorithm, right? Yeah, I'm going to skip some results. And actually today I introduced three different methods. So we implement everything as a software of Colossal AI. So now Colossal AI has attracted 40,000 stars on GitHub. Okay. Yeah, if you like, you can try these implementations in Colossal AI. Yeah. So I think the methods of LAM also had an impact. This person, Benjamin Mann, so he is the co-founder of Anthropic and also the co-first author of GPT-3. So he used a LAM in 2019. For the first time, he was able to scale transformer extra large to 128 GPUs. Right? That was before they trained GPT-3. Right? And he also wrote a blog post to introduce the LAM. Right? Okay, that's it. Thank you so much. Okay.
Okay, so we still have several minutes, so let's see whether we have any questions from the audience. You can use your microphone on the table.
Hello. Oh,
Uh,
I had a question regarding the second project, PAB. So yeah, one, how is the attention difference actually calculated? And if, let's say, you use a different metric, are the patterns still similar? And two, what layer is this attention taken from? Are you using the first layer, the last layer, or are you averaging it across all the layers? So yeah, those are my two questions.
Okay, thank you. Very good question. Yeah. Firstly, I think you can just output compute the norm, right? Because the different layers are different tensors, right? You can compute L2 norm. Yeah, you can just actually you can use maybe different tricks, but for here you can just use error to norm, right? And for us, so the key part I think is WQ, W key, WV matrices, right? You can check the difference for this also a WO matrix, right? Yeah. Okay, thank you.
Is there any other question?
Test. So regarding lamb, could you give some intuition for why the batch size affects the sharpness of the function?
Okay, yeah. So often we increase the batch size. We want to fix number of epochs, right? Like we increase the batch size by 10 times, we reduce the number of iterations by 10 times. So now, how about firstly, you have 1 million. You have 1 million opportunities to find a good local minima. Now you only have maybe 100,000, sorry, yes, 100,000 steps. You have 10% of the chance to get the same level of minima, right? I think the key idea here is you got a worse local minima, right? So I think a LAMP is a better navigation and to make you find a good minimum in fewer number of iterations. Yeah, but you ask a sharp minimum. I mean sharp minimum is a worse minimum, worse local minimum. Yeah. Okay.
So in the figures you showed, it seems to show that even at the same number of iterations,
Yeah.
using a large batch size yields more variance in the test loss.
Oh, okay.
Yeah.
Yeah. I mean, in the same number of iteration, you increase the base size by 10 times. That means your number of epochs is 10 times, right? Number of epochs, right? Yeah, right. Okay, yeah. Okay.
Okay, so is there any other questions? Okay. So actually, I have one more question. So just to try to understand the last part from the optimization perspective. So in general, like if you consider optimization, we typically have the bias error and the variance error, and the variance error is caused by the stochastic gradients, like mini-batch stochastic gradients. But for the bias error, and they're the same, if whatever you use stochastic gradients or just the full batch gradient. So I'm just wondering, okay, so why, like in your case, you're showing that, okay, if we just using the larger batch size, it can really reduce the number of iterations, because if we only look at the bias error, it will not happen.
So
Yeah, just one more thing, just consider the case that the data, they are pretty similar to each other.
okay. Yeah, I see your point. So I think so we increase batch size to 32K, right? That's I mean, if you consider the whole data distribution, right? It should 32K is still very small.
Okay.
Yeah, it's still very small.
Okay.
Even you use base size of 1 million, so potentially
Considering the
yeah,
data distribution or the total number of data points.
yes.
Okay. Got your point.
Yeah.